Yeah, it is. It's going to be possible to represent some complicated, quote unquote, complicated functions as power series, and that the beauty of representing as a power series. Power series, we're just talking more or less. We're talking powers of x, x to the first, x to the second, x to the third, maybe with a little bit of shifting involved, but it's representing any type of function, complicated type of functions, as basically an infinite polynomial. Various reasons for doing that. So let's work on doing that. The first functions that we represent, it's really based off the most basic power series there is. It's the x to the n, and we'll start at n equals 0 to infinity. And so that power series, like I said, that's just 1 plus x squared plus x cubed. Well, it turns out that we mentioned that this is really all geometric series rolled into one, if you will, because x can be any value, and so that's, if you plug in a number, that's a geometric series. 1/2 for x, that's 1/2 to the n, that's a geometric series. So any number we can plug in for x, we get a geometric series, and we know that geometric series converge when r is between 1 and -1, -1 and 1, and so now, since it is a geometric series, we haven't mentioned this, since it is a geometric series, if it converges, remember geometric series, those converge. Well, if it's, if we start at n equals 0, that's how we typically write it, a times r to the n. Remember, if it does converge, r between -1 and +1, whoops, not equal to, this equals a over 1 minus r. And again, the a would be the first term because we started n equals 0, it would be r to the 0, so your first term is a. All right, well, applying that over here, if we have x between 1 and -1, I just want to put it equal to there, then our sum, 0 to infinity of x to the n, equals, it's going to be this, isn't it? What's the a, the first term? Well, the first term would be 1. Because n equals 0, that would be the first term. We've got it right here. What's the r? Well, x is playing the role of r there, and so that expression right there becomes 1 over 1 minus x. This is our first example of representing a function as a power series. 1 over 1 minus x, that expression can be written as this power series right here. So that's the power series representation of 1 over 1 minus x. Okay, so that function, if I have y equals 1 over 1 minus x, that's the same as writing the power series x to the n starting at n equals 0. So that's our first example of it. And we're going to get a lot of mileage out of that one, for sure, and some others. But yeah, that's the idea. We're going to take an expression, function, and write it as a power series. Now again, you have to keep in mind the interval convergence. It only works for certain x's here. And in this case, it's the interval that it works for would be -1 to +1. And it can change if we change the function a little bit. Not always, but. Okay? So yeah, that's our first function we can represent as power series. Now how do we use it to get some more? Well, let's see about that. All right, so let's write 1 over 1 plus x squared as a power series. Well, hopefully you see there, it's very much related to 1 minus 1 over x, but the difference is I've got a plus here instead of a minus, and then I've got an x squared instead of an x. And so, let's do this. Let's kind of put it in this form if we can, 1 over 1 minus x, so 1 over 1 minus what would be equivalent to that? Well, it would be 1 over 1 minus x squared, right? Okay, so that being said, then since it's not 1 minus x, it's 1 minus x squared, instead of x, I've got a minus x squared there. And so this power series, instead of x, I've got minus x squared, so I want to put in minus x squared. Replace the x by minus x squared. That's what it's replaced here by. So I'll replace it here also by that. Right? Just kind of a substitution there. So, this power series is, and probably separate the alternating part out. Probably how you would see that. I mean, is it totally necessary to do that? No. But as a power series, this is what it is. Now, the interval of convergence. For that. Well, there's no need to go into all the ratio tests and all that because we already know where we started. Another way to write this is that, right? And so again, what we could do is the same thing to get this interval of convergence. Do the same thing we did for the power series there. Let's replace whatever x is here, whatever that is here. Let's replace it here too to get the interval of convergence. And solve that. Same idea. So our interval of convergence is absolute value of x is less than 1 for that. So if I replace the x by negative x squared, what does that make the interval of convergence? Well, of course, the absolute value takes care of that negative. It's always going to be positive, and really the absolute value there is not necessarily, since it's squared. Yeah, an x squared, it always goes between the negative square root and the positive square root, which in this case will be still negative 1 to 1. Yeah, it's still 1 to 1, negative 1 to 1. So, same. That one didn't change. The interval of convergence didn't change. They will though. They will change. All right. So let's see if we can do a couple others. All right. So this one's power series representation for 1 over x plus 2. Okay. So again, the idea is we want to be able to use this form right here. And that starts at n equals 0. Well, a couple of problems with this one is, first of all, it's got x plus 2, so let's flip-flop those around. Because I want it as best I can to make it look like that. Well, to make it look like that, the number in front here needs to be a 1. We got a problem here, it's 2. And so what we're going to do is make that a 1 by factoring off a 2 in front, which just means divide both by 2. So if I divide that by 2, that of course makes it the 1. But divide that by 2, it makes it x over 2. We're almost there. This is 1/2 times 1 over 1 plus x over 2. So you just kind of break off the 1/2 there separately, and then we'll let's go this way. So I can leave myself some space for another problem. All right. Okay. So we're almost there, because for this form to hold, it's got to be 1 minus x, and so I've got 1 plus x, and so again I do the minus minus thing. That's pretty well set up, isn't it? This right here well, I can use that form because now the x is minus x over 2, and so replace the x by minus x over 2 right there. With me there? Now, just to clean it up, that'd be a fine answer, but here's what they would probably do. Again, just break these all up separately. It'd be negative 1 to the n times x to the n over 2 to the n. This is one thing we could do. Just basically pull those all out separately. Write them out separately. Because, notice then, out front here, I've got 2 to the first, and on the inside I've got 2 to the n, and so those can be combined to be, if I combine those together, I have negative 1 to the n times x to the n over 2 to the n plus 1. Just combining these two right here. So that's probably how they would show that power series. Okay? And again, the interval of convergence, not too bad on these. They want the interval of convergence too. Again, the interval of convergence here, you can write it several ways, but probably the best way for the interval of convergence is think of it as the absolute value of x is less than 1. It's the interval of convergence there. Well, again, what I replaced x by down here was negative x over 2, and so if I replace it in the interval of convergence there also, I will get this, which, again, is absolute value. I can get rid of that negative there. It's always going to be positive. Multiply both sides by 2. Get the absolute value of x is less than 2. And so there we know x is trapped between 2 and negative 2. So however you want to write your interval with convergence there. Three options, I guess. I don't care which one, but. Okay. Is that all right? Okay? All right, well, here, thought I'd get another problem, but I forgot about the interval convergence. Let's get another one here. This one will be x cubed over 2x plus 1. All right, well, first of all, the top doesn't need to have an x in it, it needs to just be 1. And no difficult thing here, we're just going to pull out the x cubed to the side, if you will. So the top would just be a 1. And then again, we need to do our swapping thing there. And really the only thing here that's needed is it needs to be 1 minus, so do minus minus 2x. So there's what x would need to be replaced by. Negative 2x replaced by x in the power series, the basic power series there for 1 over 1 minus x. Yeah, this being the x cubed out here, let's break this one over here to be negative 2 to the n times x to the n. So then, yeah, we can combine those, yeah. So it would be n equals 0 to infinity, negative 2 to the n times x to the n plus 3. Probably how we would write that power series. Now this one, notice on our last one, the interval of convergence kind of expanded. It starts from -1 to +1. That last one we did was a little bigger interval of convergence, -2 to +2. Let's see what happens here. So what's the interval of convergence on this? Well, we replaced what? X by -2x. So let's replace x in our inequality here. Again, the absolute value. Get rid of the negative there. And so when we divide by 2 here, so the absolute value of x is less than 1/2. And so our interval of convergence actually shrinks here. This one only converges for x is between 1/2 and -1/2. So, any problem there? So that's not too bad.